Developing microservices. Sounds simple, right? But as developers, we know the reality, the tangled web of dependencies, the hundreds of services trying to run all of that on a local laptop, nearly impossible. Because here's the thing, your service isn't just reliant on other services and databases. Others depend on your service too, so local isn't always practical. Sure, you could use a shared staging or testing environment. It solves the dependency issue. But keeping it aligned with production, that's another challenge. And let's not even get started on isolating your work from someone else's and making sure you're not stepping on each other's toes. If you think about your inner loop or your development workflow, let's say you have a couple of services running inside a Kubernetes cluster and you need to make a change to one of them. What are the steps you go through once you've implemented your change and you want to test it? Since your service is running inside a Kubernetes cluster, you probably have to build the image first, then push the image to a registry, or if you're using a local cluster, you have to load the image to the cluster. So once you have that in place, you would have to go and restart the pods, and when they come up, you can test your changes. Depending on the size of your service, the network connection, and other factors, this typically takes in the range of minutes, and you have to do it every time you make a change. Just think to the numerous typos you can make in a day and how many times you would have to repeat this process. It's time-consuming, can be frustrating, and it definitely slows you down. You could automate some of these steps, but in the end, you won't be cutting down the time significantly. The same steps will have to happen whether you run through them manually or you have a single script that does everything for you. Let's imagine you can run your service locally. You don't have to build a Docker image, you don't have to run it inside a container, you don't have to push it to the registry, you don't have to deploy it to the cluster, and so on. In this case, the inner loop is much faster, so you still make a code change and then you build and run the application. If you've ever done any web development, you know how fast this can be. You make a change, you save the file, and your change is already in the browser. We're talking about seconds here and not minutes. How could we replicate this experience when working with microservices running inside Kubernetes? Can we run the application locally and still have access to the dependencies? And can other services access our service? A couple of years back, I wrote a short article where I talked about debugging Kubernetes applications using Istio. In the article, I explain a very simple way to run a service locally and then use some Istio configuration to make the upstream service call a service running on my laptop instead of the one running inside the cluster. This proof of concept involved a header and routing based on that header. So if the specific header was present in the request, the upstream service would route the request to the local service versus the one running inside the cluster. It worked, but it was a hack and it wasn't very practical. Today, I will look at the tool called Signadot. Signadot does exactly that and so much more. It allows you to run your services locally using a concept called a sandbox. Sandbox is an isolated environment that contains your service that you run locally while the upstream and downstream service dependencies run inside a shared or baseline environment. To make this work, Signadot tags requests with a unique sandbox routing keys and then uses sidecar proxies to route the requests to and from your local service to the baseline environment. Let's take a look at how Signadot works. So I'm starting with an empty cluster running in Azure, and the first thing that I'll do is I'll install Istio. Note that Istio is not a prerequisite for Signadot. However, Signadot does rely on a sidecar proxy to route the requests correctly. If you don't use Istio, you can use an annotation on your deployments, and then Signadot will inject a sidecar proxy for you. I'm using a default installation profile, and once the installation completes, I will label the default namespace for sidecar injection. And what this does is it just tells Istio to automatically inject a sidecar into every pod that gets deployed to this namespace. Okay, so we're ready to deploy the front end and the back end products API to the cluster. Once the pods are up and running, I will also create a virtual service and a gateway resource to expose the front-end service to the outside world. The second requirement for Signadot to work is to create a default route in a virtual service. So the default route will always point to the in-cluster service, and Signadot will be making changes to the virtual service in order to route the requests to the sandbox environment. So let's test the application. I've also set up a domain to point to the external IP address of the Istio Ingress gateway. And if I go to that URL, I'll get the response back from the front end, as well as the results from the product's API. Additionally, on the page, I'm also showing the host name where the backend request is coming from. And in this case, it's the product's pod name. Now let's say we want to make a change to the front-end service. I'll change the text on the page and then run a rebuild script that builds the image and pushes it to the registry. Once the image is pushed, I need to restart the pods in order for them to pick up the latest image that has this change, and then we have to wait for the new pod to start. Once this is done, I can open the web page and refresh it again, and I'll see the changes that I made. What I went through now was my inner loop or my development workflow. If you noticed, the change itself was very trivial and it didn't really take me a lot of time, but the majority of time was spent building and pushing the image and waiting for the pod to restart. Now let's see how we can speed this up with Signadot. So I'm on a Signadot website and I've signed up for a business plan trial, but they do offer a free starter plan as well. Anyway, the first thing that I need to do is to connect my cluster, and to do that, you have to enter your cluster name. Once you've done that, you'll get additional instructions, which include a cluster token, and we'll use this token when we're installing Signadot operator inside the cluster. So let's create the Signadot namespace and then a secret with this token. And then we can use Helm to install the Signadot operator. In addition to the Signadot operator running inside your cluster, you will also need to install the Signadot CLI. I've already done that, so my next step is to create a configuration file that will tell the CLI how to talk to the Signadot API, as well as how to run local sandboxes. So this is how the configuration file looks like. It's a simple YAML file that you save in the Signadot folder in your home directory. In the file, you're specifying the organization name and the API key. Both of those you can get on a Signadot website under settings and API keys. Note that you can also provide these two values as environment variables. Now the next section is where we tell Signadot the name of the cluster and the name of the Kubernetes context the Signadot can use to connect to the cluster. There are other advanced options you can specify here. For example, the type field and outbound and inbound fields that allow you to exclude traffic from reaching the sandbox and specifying the protocol that's used for tunneling the request to your machine. With the configuration file in place, we can now run Signadot cluster list to see the list of clusters we have access to, and as expected, there's the Azure cluster I connected to earlier. Now, since we want to run a local workload within a sandbox, we'll have to connect to the cluster first. We can do that with the Signadot local connect command. Note that the command requires elevated or root sudo permissions because it will update the hosts file and it will configure the networking in order to correctly route traffic from your computer to the cluster. We can also run the Signadot local status command to make sure that the connection is established and that everything is configured. The output will also show you the number of hosts that were added to the host file, the port that's used for tunneling the request to your machine, and the number of connected and active sandboxes. So let's just list the host file as well so you can see the entries that were created. This is basically a host name, a combination of service name and namespace plus the .svc.cluster.local suffix, and this is created for each service that's running inside your cluster. As a next step, we will create a sandbox YAML configuration file. Now, note that these steps are more or less a one-time thing. You would create and run them once, and then once you have the sandbox running, you can work on your service locally, make changes, test it right away without running any extra commands. So there's no building of the images or restarting the pods. So here's how the configuration file looks like for a sandbox. Note that it's templatized, so when we use the CLI to create the sandbox, we'll pass in the cluster name and the service name, but you could also templatize it further to provide the ports if you want to. But basically what we're saying with this file here is that we're creating a sandbox and we'll run a local version of the in-cluster workload. So in the mappings field, we're saying that we want to map the port for or of the in-cluster workload, the port that in-cluster workload is listening on, so port 80, to localhost 8000. So we're telling Signadot that whenever someone requests the workload on port 80 inside the cluster, it should route the traffic to localhost 8000, provided the request also has that routing key. Now, to create a sandbox, we'll run the Signadot sandbox apply command, pass in this YAML file, and then specify the two parameters, the cluster name and the service name. Now, this takes a second, and it will give us a routing key, and this is the key that's used to route the request to Sandbox. Okay, so we're at the point where we're connected to Signadot, we created a sandbox, and we have a routing key. Now remember when I talked about Istio and how the default route is required for each service. So let's take a look at how Signadot has updated the virtual service for the product's Kubernetes service. Now, the virtual service still has that default route. So that's the route that will always be invoked and applied and will always route to the Kubernetes service that's running inside the cluster. However, notice this new route that got added with a bunch of header value matches. So if the request has any of these headers set with the value of the routing key, the request gets routed to the version of the service that's running inside the sandbox. Now, for this to work, for this context propagation to work, we have to make sure that our services are propagating at least one of these headers. This is also a requirement for getting end-to-end tracing, distributed tracing in Istio to work. So the proxies will intercept the incoming traffic and headers. However, the service itself has to propagate the headers to the outgoing requests that it makes. Now, also notice the route destination is a host name that's a combination of the service name and the routing key. So this is another thing that Signadot created. This is not a Kubernetes service. Instead, what Signadot created was a service entry that has that host name. So if you look at the service entries, we'll see that there's a new service entry that was created with that same host name that's used in the virtual service. So let's take a look at the details. The service entry points to a specific IP address, and if we look at the pods that have that IP address set, we'll see that it's an IP address of the tunnel proxy, and this is one of the components that got installed with Signadot. Now, to quickly recap, when we send a request with the routing key and a header through Ingress Gateway to the front-end application, the front-end application will make sure to propagate all those headers to the outgoing requests. So when it makes that request to the product service, one of the matches in the virtual service will evaluate to true and will route the traffic to the tunnel proxy. And then the tunnel proxy will do its magic and it will route the traffic to localhost 8000, where our local version of the product service is running. So let's run the local instance of the products API and open up the website. Notice the requests are still going through to the baseline version of the products API that's running inside the cluster, and that's expected. So let's get that routing key again, and we'll see how we can use it to route the requests to the sandbox version. I'll open another terminal just to keep the products API running, and then just run the sandbox get command to get that routing key again. Armed with the routing key, I can use the mod header extension, and this extension allows me to put custom headers into requests. And I'll just paste in the routing key and refresh the page. Now notice that this time the response on the page is different because the response is actually coming from the service that's running on my laptop. Also notice the host name, which in this case is set to PeterJM1 Home, and it's not the name of the pod as it was before. So at this point, we have the traffic going from the front-end service running inside the cluster to a downstream dependency running on my laptop. Now, if I make a change to the product's API, I can test it right away without having to build and push the image and restart any of the pods. It's just a matter of saving the file, refreshing the page in the browser. Now, I also have the node mod running, so node mod will automatically restart my application whenever I make a change. However, you can use any other tool that does the same thing. So this really feels like web development. You make a change, save the file, refresh the page, even though there can be multiple services behind the scenes, all running in a shared cluster that can be used by multiple developers at the same time. Local development is just one of the use cases for Signadot. Another big one is using it as a part of the CI and creating sandbox preview environments for each pull request. In that case, there's no local service per se, but a similar configuration can be used where you would provide a set of customizations that Signadot will apply to a selected deployment. They're using a term called fork, where you're forking a baseline deployment and customizing it with, let's say, a different image name or a different image tag, additional environment variables, and so on. Now, you might wonder about dependencies such as databases and how does Signadot handle those? So there's a concept of resource plugins that allow you to run a workflow, basically a set of steps that you can run before a sandbox is created and right before it gets destroyed. So this allows you to create and, let's say, configure a test database, run migrations, and then use any of those outputs from the workload in the sandbox configuration. So if you continue with the database example, you would create a database and then use a connection string that you get as part of creating the database. You would use that as an environment variable in the sandbox configuration. That way, your forked service can connect to an instance of a database that's running in Sandbox without impacting the actual database from the baseline environment. Another feature is route groups, where you can specify labels and match multiple Sandbox environments. So let's say there are multiple developers working on the same feature that spans multiple services. Each developer would create their sandbox with a specific label that allows routing to happen across multiple sandboxes. This is incredibly valuable, especially for larger teams or complex microservices architectures, where you need to ensure that the changes you're making don't break the functionality of other services. So instead of waiting for changes to be merged and discovering issues at that point, you can test your changes in isolation and make sure they work as expected, even before getting to a CI, PR, or any of those later stages. So this reduces risks, saves time, and makes the whole development process way more efficient. To wrap it up, the challenges of microservices development in Kubernetes are real. The complexities of dependencies, ensuring your changes don't negatively impact other services, and the time-consuming process of building, deploying, and redeploying your service to a cluster, all those can slow everyone down. Now, tools like Signadot provide an alternative approach which makes your inner loop, your development workflow, much smoother, faster, and more efficient. Now, there are a couple of things you should keep in mind when deciding whether Signadot is a good fit for you or your team. So Signadot does require a sidecar proxy to be injected into each pod. So if you're already using Istio, which you should, that's great, you're ready to go. However, if you're not using it, you'll have to consider the overhead of running a sidecar proxy in each pod, be it either by adopting Istio or using the annotation that Signadot provides and the proxy they configure, run, and maintain, which brings me to the next point. Signadot is not open sourced, which isn't necessarily an issue. However, some other tools such as telepresence are open sourced. Now, all this comes down to your preference of using open source tools versus commercial tools. Note that though that there is a free plan available for Signadot, so you can try it out and see if it's a good fit for your team or not. All in all, I think it's definitely a tool worth checking out, and I'm looking forward to see how it evolves. If you're interested in trying it out, check out the link in the description below and let me know what you think in the comments.